All right, I've been hyping this section up for a while, and we're just going to jump right into it. I'm going to show you a problem, and I'm going to outline some steps, and that's going to be the process. That's going to be logarithmic differentiation. All right, so here's the motivation. What if I wanted to take the derivative of y equals x times the square root of 2x plus 1 over e to the x times sine cubed of x? Or again, what if I wanted to take the derivative of something like that? The second thing, we have no tools to find the derivative of. The first one we do, right? You could use the quotient rule. And then for the derivative of the top, you'd have to use the product rule and the chain rule and the power rule. And the bottom, you'd have to use the rules for exponentials and the chain rule and the product rule and derivative of sine. It would be a nightmare. And I'm sure I've given you a couple nightmares in this class, but probably nothing as big as this one, if I made you do this with old techniques. But watch this. Remember the one-to-one property for logarithms. Logarithms are one-to-one functions, which means that the above is exactly identical to this. These are the exact same things. Let's say that x is positive. Because as long as this is defined, they're the same things. So as long as x is positive, they are the same thing. Now this bottom thing, you might say, Jason, you just made it worse. But remember back to our earlier video, 3.9.2. Somewhere. If we're trying to take the derivative of a logarithm, we should always remember to simplify first. So over here, oh, what is that doing there? Over here, we want to take the derivative. Let's simplify. So the natural log of y equals the natural log of x. I'm going to do things a little faster. You may want to review properties of logarithms. So again, we add together everything on the top. The square root is an exponent of 1/2, which comes out in front, minus the natural log of everything in the bottom. Like so. And we can keep on simplifying. Let's keep on simplifying. We got the natural log of x. Here, let's actually not simplify in this step. I want to make it more obvious. There we go. We're writing the square root as an exponent of 1/2. We'll take it out here. The natural log of e to the x, those are inverse functions. Those cancel just to x. Natural log e to the x. Inverse functions. And so this is the fully simplified version, and this isn't extraordinarily nice. But I think the right-hand side here is much nicer than before. No product rule necessary, no quotient rule necessary. We have like 2 chain rules, but they're not even super messy chain rules, I think. So in logarithmic differentiation, this is exactly what it's all about. The first step of logarithmic differentiation is to ln both sides and simplify. Now we're ready for the second. And again, I haven't exactly told you what logarithmic differentiation is. I just want to kind of show you an example first. We're going to take the natural log of both sides and simplify. And then we're going to use implicit differentiation to find y prime. Okay. So let's take the derivative of both sides. So the derivative of the left-hand side with respect to x, the derivative of natural log, derivative of any logarithm is the reciprocal of the inside, and then you might need a natural log of the base. But the base here is e, so we have a natural log of e right here. It's implicit differentiation, so we have to multiply it by dy dx. because we're taking the derivative with respect to x. Derivative of the right-hand side, derivative of natural log is the reciprocal function. Constant multiple rule, derivative of the natural log of 2x plus 1, reciprocal. Chain rule, derivative of 2x plus 1 is 2. Derivative of x is 1, minus constant multiple rule, 3 times the derivative of the natural log of sine of x, reciprocal. Chain rule. That's implicit differentiation. We'll want to simplify a little bit and get y over to the other side. So let's multiply both sides by y. And let's simplify this inside. First part is just 1 over x. Second part cancels. And it's just 1 over 2x plus 1. Third part is just that. And fourth part, just like before, cosine over sine is cotangent. We're almost done. We've almost found the derivative of this original function. Because this is the same thing as this. And we found the derivative of that bottom thing with not many steps at all. So we actually have almost found the derivative of this whole messy thing. The last part of logarithmic differentiation is to substitute y back out. Substitute y. So y was this whole messy thing. So let's replace it. Y prime, the derivative of y with respect to x, is y, which is, this is y. I'm writing down y right now. Times the same insides that we have before. And again, you could leave it in this form. And I guarantee you that what we just did, oh, my head is in the way. I guarantee that what we just did is way nicer than trying to do it the old-fashioned way. If you're bored, try to do it the old-fashioned way. Try to do this without logarithmic differentiation. Try to find this derivative with the quotient rule and the product rule and the chain rule. So what is logarithmic differentiation? I showed you, but what actually is it? What are we doing? If we have a really messy function, or sometimes a function that we don't even know how to take the derivative of anyway, sometimes it's easier to, instead of taking the derivative of the function directly, take the derivative of the logarithm. Logarithmic differentiation is just taking the derivative of the logarithm to make use of all of these really nice properties of logarithms that we can use to simplify things. So all you do for all logarithmic differentiation is, it's just a process to make things easier, where we take the natural log of both sides, simplify, and then use implicit differentiation to find y prime. And the final step is always going to be substituting y back. So let's see this in action again. Example 7. Differentiate the following. Part A. Y equals x to the x. Power rule doesn't work here. It's not a monomial. It's not a power function. It's not an exponential function either. We can't do it that way. There is no tool other than logarithmic differentiation that works to take the derivative of this function. And again, let's assume that x is positive. We're going to assume that because if you look at this function, you may remember it from the beginning of this section. If x isn't positive, we have some really weird nonsense going on to the left, which actually is not showing up anymore. Why? Because, I don't know. Let's just assume x is positive. Desmos is sick of me, sick of dealing with my garbage. So To take the derivative, we'll follow these steps. Step 1, take the natural log of both sides and simplify. As long as like the domain restriction is covered, these two things are exactly the same. So the natural log of y, we can use properties of natural log to write this as x times the natural log of x. There we go. Step 1 complete. Step 2, use implicit differentiation to find y prime. So we take the derivative of both sides. The left-hand side derivative of natural log is the reciprocal, and we have to use the chain rule. Derivative of the right-hand side is going to require the product rule, where the first function is x, its derivative is 1. The second function is a natural log of x, and its derivative is 1 over x. Product rule says the derivative of the first function. Nope, I'm going to make a mistake if I do it. F prime g plus fg prime. Just write it out. Just write it out. So we have 1 over y dy dx equals f prime, which is 1, times g, the natural log of x, plus f, x, times g prime, 1 over x. Oh, this is nice. X times 1 over x cancels out, and be very careful, it cancels out to 1, so it doesn't completely disappear. We can multiply both sides by y. dy dx is equal to y times the natural log of x plus 1. That brings us to our final step. Substitute y. Y is x to the x. So y prime is equal to y, which is x to the x, times the natural log of x plus 1. And that is a way to take the derivative here. It's kind of a little interesting, because if we treated this like an exponential function, it's not. It's a weird function. If we thought it was an exponential function and we tried to take the derivative, we would say, okay, the derivative of an exponential function is itself times the natural log of the base. And actually, that's almost right. Right? These are pretty similar. It's not true, but it's actually kind of close to what we might have guessed. Anyway, let's do 2 more problems for extra practice. Again, you have all the tools right now if you want to jump straight into the homework. But if you want extra practice, you can watch 2 more examples. Part B. Y equals 2 to the x to the 4th, 2 times x to the 4th plus 1 times the tangent of x. Okay, we can't use the power rule. Power rule is only if the exponent's a constant. And it's not an exponential function because we have it's the same like a. We have a function in the bottom and a function in the top. This one's going to be a bit tricky. We're going to need to use logarithmic differentiation. There is literally no other way to take the derivative of this function. What does this function look like? This has got to be another really weird one, right? Y equals 2x to the 4th plus 1 raised to the exponent. Wait, what's going on here? Raised to the exponent of the tangent of x. All right. Kind of wacky. As we expected. Let's find its slope. So first step, take the natural log of both sides and simplify. So when you take the natural log, we have the natural log of the left-hand side equals the natural log of the right-hand side. Be careful with your parentheses here. And we'll use properties of natural logs to simplify. The exponent can come out in front of the natural log. We're going to get the tangent of x times the natural log of 2x to the 4th plus 1. And that's it. It doesn't simplify any nicer than that because of this pesky little addition sign. Let's Step 2, use implicit differentiation to take d dx of both sides. Derivative of the right-hand side is the reciprocal, and then use the chain rule to get dy dx. Derivative of the right-hand side, again, is going to require the product rule, where the first thing is tangent. The derivative of that first thing is secant squared of x. The second thing is the natural log of 2x to the fourth plus 1. And the derivative of that second thing is the reciprocal times natural log of the base, which is just 1. Natural log is that nice special form. And then we have to use the chain rule to multiply by the derivative, which is bring down the power, 8x cubed, like so. So it's f prime g plus fg prime. Again, even when I like skipping steps, I'm making myself write this because I make a lot more mistakes when I don't. So 1 over y times y prime is f prime, which is secant squared of x, times g, which is the natural log of 2x to the fourth plus 1, plus f, which is tangent of x, times g prime, which is going to get covered by my head. 8x cubed over 2x to the fourth plus 1. We'll take this to the next page. Multiply both sides by y. Get y prime is equal to y times all of this. Secant squared x, natural log of 2x to the fourth plus 1. We're not going to try to simplify this at all. Plus 8x cubed times the tangent of x, all over 2 to the x, 2 times x to the fourth plus 1. And then the last step for implicit differentiation is to replace what y is. Y was that wacky thing, 2x to the fourth plus 1, raised to the tangent of x power. Now we still have all of this other inner garbage from before. All right, so yes, it's messy. Yes, this doesn't look nice. Yes, there's a lot going on. But logarithmic differentiation gives us a tool to find a derivative. Not a pretty derivative, but it gives us a way to find the derivative that we don't have any other way of taking this derivative. There's no other way to take this derivative other than this. And yeah, it's messy, but it's possible. And that's why I think it's such a cool tool. Half of it is used for making problems easier, which I always like. And the other half is used to make problems possible, which is also nice. Let's do one more. We're going to end. This is a nice cool down. We've already done our 10 mile run. And now we're going to do some cool down. R, just some number that's not 0. We're going to use, yeah. This is the power rule. We know what the answer should be. Let's use logarithmic differentiation for practice. Natural log both sides. Take the derivative. Oh, simplify first. That exponent comes down. Take the derivative of both sides. I'm going to write y prime this time. Constant multiple rule says this is the derivative of that right-hand side. Multiply both sides by y. And replace out y. Y is x to the r. This is another way of getting to the power rule. Another way of proving the power rule. You might say, Jason, this looks nothing like the power rule. Give me 1 second. We could rewrite this as x to the r times x to the negative 1, right? R divided by x is r times x to the negative 1. Put the r in front. We have two exponential functions with the same base. We can add their exponents. Oh, now that looks like the power rule. Yeah, there it is. Nice. That's logarithmic differentiation. I hope you think it's cool. You might hate doing it, but I hope you can appreciate that it's kind of a really handy tool, at least. Let me know if you have questions, and have a great day.